Hello everyone, it's May 31st. It's the last day of May. Um, we had two tough questions. Well, actually it's not that tough compared to 2 weeks ago. So today I expect to be something easy. Let's see. Uh, wow, doesn't look easy to me. Have three hints. Given an array of strings, products, and a string search word, we want to design a system that suggests at most three product names from products after each character of search word is typed. Suggested products should have common prefix with the search word. If there are more than three products with a common prefix, return the three lexicographically minimum. Wait, three graphically minimums products. What does that mean? Return a list of the suggested products after each character of search word is typed. It's actually quite interesting problem. Product sorted lexicographically, right? So we sort it first, and then after typing M, we're gonna go. We should use our mobile, money pot, and monitor Y. After typing, hold on. After typing M and MO, all products match, and we show user M. Wait, why? Oh, it's sorted. So mobile, money pot, and monitor. Okay, so these three. So basically it's sorted, and I get the first three out. MO, first three out, and MOU, which is mouse and mousepad, and MOUSE. So basically what we're saying is we're going to product length. That's going to be a try for sure. And product I dot length, the word can be this long. All characters are lowercase. Search word, lowercase. Okay, so basically we're gonna create a giant try, and then as we search, we type the first one, we are going to return, right? And then can we like save the state where it is? I mean, let's just do this. Sort it first, of course. So from the root coming out is M. Everybody start with M. And then we have this one O, right? Everybody's O, so O. And next one we have B, so B. And I, B, I, L, E. Right? So that's that. And then this one is MO. We have N. All right, N, E, Y, P, O, T. Money pot. And then monitor MON, I, monitor T, O, R. Next one is mouse, M-O, so we branch out to U, and then S, and then E, and the last one, mouse pad, mouse, and we just keep going, P, A, D. Right, so apparently we need to store a list at each node. like all the words that's, so after M, we're gonna store mobile everything. Oh yeah, so at each node, we need to store the entire list that contains the words, right? Entire list. And then when we search, we just pick the first three. Pick the first three. Alright, seems like it. Let's give it a shot. Let's give it a shot. I think, if I'm not mistaken, this should just be a try. What did you do, man? Come on. This is made 301, huh? Yeah, just a little typo. Should be made the 31st. Alright, now we can do this. Pull it out. Okay, V. Okay, so we're gonna do a try. It's going to be, we're gonna use the default dict from collections, import default dict. Alright, and then there's gonna be default dict lambda default dict. I think that's the try. Oh, actually no. We also need another thing inside the default dict. We can call it, yeah, we can call it a name. Hold on. How do you want to do it? So each one will be default dict. No, this is not gonna work because we need to store. We need to store a list of words, and those are not default dict. We have to use a try node. Right, try node. Def initiate self. What do we initiate? Let's just do like this. So in the safe self.children, right? Self.children is going to be a dictionary, and yeah, and self dot matches. Let's call it matches. It's going to be this. Okay. So try equals try node, right? That's a root try node, and we're gonna first do products dot sort. Actually, we don't have to. I think I can just say for prod in sorted products, right? And then for letter in prod, if letter not in try dot, we'll actually have to use a node. Node equals try. So not in. Actually, no. This one's gonna be here. Each product we specify new node. Dot children, right? Then we say node dot children letter equals a new try node, right? And then we say node dot matches dot append product, right? Yes, because we need to append on every single level. So the node has to append the product, and for each one, and then letter. So we're gonna say node equals node dot children letter. So we go to the next node. right? Next, blah 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 until the end. Okay, that's that. So we produce everything, and now we're gonna search word. So the rest gonna be this. I'll just say for letter in search word, and then we go again. Node equals try. So letter in search word, rest.append, node dot matches. Oh, hold on. What if there's no match? Yeah, this try is the parent node. Try is the parent node. So we have to do node. Wait, how do we handle this? This is not right. Because this is the parent node, right? Parent node shouldn't contain anything. The word should be appended after. Hold on. So we start with this, right? And then we give a letter, and then in that belongs to the letter. The match should be belong to the letter, right? It should be belonging to the letter. So this is the root, right? This is the root. So in the first one, I got confused on how the try works. And the letter is not in node.children, right? Then node.children letter equals this. And then we need to move the node first. Move the node first, and then we put the words in it. And then we'll go to the next one. And we see if node, yeah, we move the node first, right? So here's the same thing. So we say, if node, if not node, if letter in node.children, right? Node equals node.children letter, right? If it's not, node equals node.children letter, and then rest so I can append node.matches the first three. And if it's not, then we just going to, if letter is not in else, I think rest just dot append an empty list, right? And now we'll go to the next one, and node already updated. Yeah, I think this is true because if at one time that the letter is not in node.children, that means that's the end of the search for this path. Every future ones, it's not gonna return anything. Yeah, so it's like if the search will we go to the end, so any further will just be empty. So I'm gonna return rest. All right, let's give it a shot. So we're gonna have, this is our first test case. All right, we don't need this. And as usual, clean up this. And also clean up this. So that's the first one. Oh man, I have the output. Wow, output will be hard to handle. I'm gonna do, yeah, that's what I'm gonna do. Next one. Yeah, and then the final one. Yeah, and then I think there's one more. Yep, there we go. So we also have to handle all of this. All this turn into here, and also all the commas. Starting from here, some comma, right, comma, 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 and the last comma. Okay, that's the first test case. Second test case. Havana. Havana. And Havana as well. Therefore, we should have the same word appearing in all of the test case. Like that. Okay. So, same thing. Okay, the second test case. Third test case. Oh, it's a complicated test case. This. And the search word is bags. The result is all that. Okay. And this one. Oh. Commas. So, last test case. Still gonna go Havana, but the actual word is different. Therefore, the result is a bunch of empty things. Okay, so that's a test case. Change the input. So what we're gonna have is products, search word, and this is going to be suggested products, product search word, and try it. Oh, it passed every single one of them. All right, give us some confidence. So you're going to put it here. Here we go. Pending, judging, runtime error. Probably some edge case we didn't consider. Runtime error. Name try node is not defined. Oh, that's not edge case. It's forgot to paste in this one. There we go. All right, I'll try it again. Pending. Oh, why pending so long? Oh, I got a wrong answer. I got a wrong answer. Okay. This is going to be. Oh, this is not going to be easy to debug. I got a wrong answer. I want to take a look at the answer, the wrong answer I have. But I mean, it's not gonna help. I just want to take a look. It's a medium question. I don't think it's that hard. I don't know what happened. Wrong answer. Test case. Oh my gosh. Jeez. Nah, this is not helping. It's not helping at all. Wait, so what is wrong? Man, this is. I need to have a diff. I don't think diff checker. This is my output, and this is the expected output. Find diff. Oh my god. Oh my god. Wait, does that mean that diff in every single one of them? No, this is not helping. I mean, something is not right, right? Something is not right. For sure, something is not right. I mean, as we going through this, does that mean like, I don't know, we're sorted again? Is that like, I mean, one thing that I think might be a factor is as we go through, because I thought we go through in a sorted order, right? And then, yeah, if I go through this in sorted order, and I put it in every match, and I'll go again, and we'll put it in every match, they shall follow the graphical order. No, I don't think, I doubt it. This is the top 3. Because these all pass, right? I think again, we build a try, right? We build a try, and we go through assorted products, and each product coming in, and I break down its letters, and as I break down its letters, I put them in each individual node. Each individual node. Yes, I put them in each individual node. And then I think I need to play with this. Like just I don't know. G F W. I don't know. Just trying different things. Hey, look at this. This is not correct. Look. How? I got the first 3 out, and I got this. How I... Oh, wow, this is a bug. What is this? So G, right? G will be these 3, and then R. There's no R. Right here is no R. So next letter is R. R is not in the node, so rest in append. Oh, because R is not, and then eventually I hit, like, well, I had an E, and then I come back in again. I think here, I'm going to change here. So when this is not children, right? When letter is not children, we just ended it, right? We just end it by saying how do we end it? So we're gonna say I in enumerate. So I kind of know how many to append, right? So if it's not, we just say rest dot extend for in range len search word minus I, and then break. Okay, so we're gonna do this. Let's see if it works. If I run code, once it doesn't match, now we just immediately end. I is not defined because I haven't changed this one yet. Okay. Total number minus, total is 301, and that is correct. That is correct. Okay, try it again. Pending. Accepted. Yes. 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 So it's just a little bug over here because I don't really think there's any issue on the beginning. All right, we did find the bug ourselves. It's good. So first, build a try. We also need to keep track of each word in each product that hits try node. If we go through the products in ascending order, then the product list in each try node will also follow ascending order. Then we loop through each letter in search word and record the associated products at each try node. The tricky part that got me is that once the try node is exhausted, we should immediately add empty lists to the result. Right. So build a try, I think, is O and M. That's to build a try. And to go through will be plus L. Let's call it that. So where N is the length of products, M the length, the average length of product, and L is the length of search word. What is our runtime? I got a 296 milliseconds or 44% ranking. Mediocre, exactly, fitting my name. Okay, so this one's done. We can go check, see the clever solutions. Oh, I have a solution here. Yeah, I think we'll probably get a bonus because this is the last day of May. We get a 150 Only get 50 points for completing the May challenge. Binary search. Hi. Interesting. Oh, that was faster. On log n plus om log n. Om log n. Try and DFS. OM to build the try. Total number of characters. Finds representative node. Space complexity. And is the number of nodes in the try. Yeah. It's a simpler version. Okay, so let's see if the try is what we think it is. Whenever we come across questions, multiple strings, think with a try. As for sorted results, if you look closely, a try word is represented by its pre-ordered traversal. It is also worth noting that pre-ordered traversal of a try will always result in a sorted traversal of results. So all we need to do is limit the word traversal to 3. Oh, that's different from what I do. So so I think they are traverse every single time. So we traverse. So we have this and we just traverse. I see. Create a try. Iterate each character, adding to the search for after adding the current character. The prefix, traverse the try pointer to the node representing prefix. Now traverse the tree from the current pointer in a pre-order fashion and record whenever we encounter a complete word. Limit the result to 3 and return DFS once we reach this limit. I think it's different. We waste a lot of space, I think. That's the conclusion. I do think we waste a lot of space. 21. Because we store the results. Yeah, we waste a lot of space. What they say is we create a try, which can be created easily without a try node, and the try can be easily created. And when we have the actual word, we want to traverse, so we simply traverse. We're given the current one, we're given the prefix, and we go to the node that ends with a prefix, and from there we traverse pre-order, which means I think it's the left. No, it's root left right, right? Root left right, root left right. So that will automatically give you in sorted words. Oh wow, that's long. Yeah, we can try it. We can try this. How does DFS work? So the DFS will be we record 3 times and then we just return, right? Yeah, you put a list in it, and every time we just add. At the end, we push it to it, and then go back. We try to go to the next one, go back, and every time we go, we need to check the length of the list. And the list we're mutating the list every single time. We check for that, and once the length becomes 3, then we just terminate it. Good. I think this is probably also easier to write because we can use Yeah, traversal. Okay, let's look at the time complexity. So time complexity, the builder try is m, right? And then for each prefix, we find its representative node in len prefix, and DFS to find at most 3, which is O1 operation. Thus, the overall complexity is dominated by the time required to build a try. Len prefix. Len prefix times 3, right? Len prefix times 3. Let's say they're dominated. No, that's fine. Yeah, the complexity is low. The space complexity is low. Which means in our case, let's try to write it. So in this case, I think we can use default dict. You can say try equals default dict lambda default dict, right? And then for prod and products, sorted products, right? I'm gonna sort it first, and then I'll be back. All right, I'm back. So same thing, node equals try, and then for letter in prod, I'm gonna say if letter not in node, yeah, if letter not in node, then if letter not in node, node letter equals try. Ah, wait, how do we do this? Default dict. No, it's already set up. It's already set up. It's if it's not in. No, I don't think I need to do this. It's already set up. So letter in prod, right? We just say node equals node letter. Yeah, we'll go to the next one. For each letter, we'll go to the next one, go to the next one. And then that should be the building phase. And now we just need DFS node, and we also need matches. Matches. That's going to be a list of str. Oh, not returning anything. Are we returning anything? We can. We're going to return a boolean, so to say if it's good or bad. So once we reach what? Like if how? Well, we know it's the end. We say if not node dot. If not node, right? If node is an empty thing, we probably also need to pass current string, current match, right? I'm going to pass the current match, which is str, right? So, and then we try to go to the next one, right? So, current letter we put into the match, and then we go to the next one. And the next one, if not node, then we say matches dot append match, right? matches.append match, and then we can put a result here. The result is going to be this. So matches appended, yeah, and then we say if len matches equals 3, then we say res.append matches copy it. No, we don't have to copy. I think we can just do it. We can just append it. It's fine. Because this DFS is going to be run for each prefix, right? For each prefix, we're going to run it. So it's slightly different for each one. So I can just append and then return false, right? Otherwise, we're going to return true. True means keep going, right? So now it is node, right? Node has something. So we say if a node has something, then we're gonna, what are we going to do? We're gonna add, so we're gonna say match, we're gonna say a new match equals match plus what? Actually, it shouldn't be node, right? Pass the next node. Hold on. We are going down, so from the root, and go for each. No, I think it should be from the root, right? And then we go down each path. It's the passage contains the letter. The node doesn't contain the letter, so if you hold the node, it's not gonna work. So it should be from the node. We'll go to the next level, right? We'll go to the next level, and that's when we put yeah, I think it's this. I think it's this. For letter next node in node dot items, right? New match equals match plus letter, and then DFS. I'm gonna go to the next node, new match, and matches, right? And when you say if it's if it's true, then we keep going. If it's not true, which means we're done, then we're gonna return false as well, right? We're gonna return false as well. And we're gonna go, if it's true, that means we haven't done yet, so we go back, we go try to find the next one, and try to find the next one, try to find the next one. New match will be this, and we're going here. If we're done here, what do we return? We return true, right? Because everything is true. Like this one is, hold up. So we keep going to the end, right? And then if we add a match, it's true. And we go, everything is true. Then that means we keep going. So I think, yeah, this is going to be true, right? This is going to be true. So that's a DFS. We're just going to call for letter in search word, right? For letter in search word, We have a try. So again, we're going to say node equals try. Right? So for letter in the search word, we're going to say, what do we say? We say node This is the first letter, right? It's the first letter. The first letter. How do we say? We're gonna pass the root, right? We're gonna pass the root node in, a match if it's empty, and then we just say for a letter in this just feels a little bit strange, huh? So the initiation should be matches the first one, right? And then the node should be after I match the first one. Yeah, after I match the first one. So it's gonna be if letter is not in node, right? Letter is not in node. That means we are done. Hold up. If letter is not in the node, that means we are done. If letter is not in node, we keep going, and a letter is not in node. So that's when we say res.extend for this in range len search word minus I. Right? It's the same logic. So we're going to say I letter in enumerate search word and break. Right? Else letter in node. So if letter in node, then we're gonna go DFS, right? If letter in node, so we're gonna DFS. DFS current match the node, which should be the next one. So it's node letter, right? And then the current match will be search word to I. Actually, I plus 1 because we're not including I. And matches will be just empty. And then we're going to go through this DFS. And after DFS done, we're going to move on to the next node. So we say node equals node letter. So move on to the next one. And then come into the letter and try to see if the letter is in this one. And if it is, then we go for that. And then we're going to return res. So this is a little bit convoluted. I'm not sure. Let's see. Nope, I don't think this is correct. We have issues. There are no type variables left in collections by default. Oh. Don't know what that means. Line 55. Oh, we have trouble here. There are no type variables left in, what does that mean? There's no type variables. try is let's try. I think let's try instead of yeah. There you go. That's one pass. So we now have a problem here. Maximum depth. Okay, so we need to end it better. Return. And then if I get an information which is true, then I keep going. But if I get a false, then I return false. And our previous one was false. Yeah, this is convoluted. So let's just make it simpler, right? We'll make it simpler. So we say matches.append a match, right? Then we return, right? We append it, then we return. And yeah, no matter what, we append and return. And we do it here. So for letter in this, and then we're gonna do a DFS, right? We're gonna do a DFS. After we do DFS, we're gonna check, right? We're gonna say if len matches equals 3, then we return, right? If it's not, we keep going. Now we keep going, and finally this is gonna return no matter what. Actually, we don't even need to write it here. So we're gonna do this. Let's try it again. Still maximum reached. That's interesting. Why? Okay, let's try. Let's matches.append. Also, if len matches equals 3, or in the rest.append, let's need to append matches. Right, rest.append matches. And we'll return. And if it's equal to 3, so let's see. Let's just every time coming in, let's just print matches. Let's see what happens. Empty, empty, empty. It's all empty. That's not right, huh? So all we start is let's first see the try. Let's see the try. If the try make any sense. Okay, try I think it makes sense. Okay, try I think it makes sense. It's here, right? So we say if letter is not in node, then we end it. It's fine. If letter is, then we DFS, right? DFS node letter. So we get to the node, right? After the letter, and the match currently is just whatever the letter we currently have. We have an empty list, and then we go in and node, yes, if node, so a letter and a next node, right? We have a letter and next node in here, and then new match equals match plus the letter, right? So we put a new match in here, the next node in here, and the total matches in here. Now we keep going, we keep going, until eventually we hit a letter. The next node is going to be empty list. So I put it here, and the matches dot append the current match, yeah. And then if it's equal to 3, I'll push matches in, and then we'll return. So I'll return here. Now we check the matches size, and we say if the size is 3. Then we say we terminate it. So we go back up, Why would it? I don't know, man. Let's try here. Print matches. Okay, I think this one. Wait, is this never hit? If like not no never hit. So we know it's going to be a try, which is a default dict. Len node. 15. Always 15. What the hell? Node dot keys. Mobile. It looks to me the problem is everyone's a try. I think this is fine, right? So node is a try, right? So if for letter in the product, node move to node letter, right? And then come back up. This is weird. Every single one have the key. Why would you have so many keys? It looks to me as the try is not created correctly. I think this is all the letters. Hold up, I think the problem might be with the try itself. So we are going to investigate how the try is going. Okay, so let's print try dot keys. All right. Yeah, the try is not right. Oh, I refer to try itself, which means I cannot refer to try itself. Is how this supposed to be? Ugh. Yeah, so everybody's to the try itself, but I want. It's supposed to be like a copy of the try. Like, can we do this? I don't think this works. No, I forgot how this one's done. Shoot, do this? No, there's no slice. Try is a default dict, right? And now everybody will be another default dict. I used to know, but I don't anymore. I don't remember. We're gonna create a try. How is this one? How does the try work? Man, this is very frustrating. I used to know. It is lambda, and it's not default dict. It's not default dict. Oh man. Yeah, it's a default dict, right? So the value is going to be a new try. Yeah, it's going to be a new try. That's correct. We're going to be a new try, and then we say for each product, right? and we have the node going back to the root of the try, and we say for each letter, the node or equals node letter. Okay, so that's a new node. Right, that's a new node equals node.letter. Try.keys. The first try should only have m. But now we are having all of them because we're referring to the same try. Node equals try. Node letter. So this put. What is node letter? Node letter is going to be a new try, right? It's going to be a new try, which is going to be a new default dict. Ah, I forgot. Default dict try. How? Oh, yeah, I mean this one. The try trick. I forgot how to do this. Just try return the product. Okay, that's not how I remember. What is the... Nope. This is not how I remember it. Nope, 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 nope. I remember there's a very elegant way. Very elegant. Is this one? I don't know. It looks like it is. Looks like it is. Yeah, I mean, referring to itself definitely is not working. So what he's saying is, but hold on. I think I remember. It's lambda here. Try is a lambda. Yes. Try is a lambda. And then we're going to return a default dict that contains try. This function has no attribute keys. Oh, yes, then it has no attribute keys. So for product in this, yes, I think this is the trick. Node is gonna be when I call it. And if I'm gonna call it a try. So node and equals this. Default is not callable. I guess it's not. My God. So a try is a function, and it returns a default dict. So this should still be right. There we go. I think now we got it. So I think I need to do root equals try, right? So I have a root. So no, it should be a root, and then I can print the root. That looks more promising. Root.keys. Yes. That looks way more promising than earlier. Okay, so now I think we can handle, so have a node, right? The node is that default dict, that's a default dict, and append if it's this will return, and if it's this will return. Okay, so node equals root, right? Then if this not, and then we're gonna say node letter, and node equals, try it. Fail, answer, result. Okay, so we at least print something out. Mobile multiply monitor, mobile multiply monitor. So we didn't print out the remaining because we say equals 3. Huh. And I think it's here, right? This is at the end. We append it, and then we execute to the end. We execute to the end. Oh. Oh, I think we don't append, right? We don't append here. We just return, right? If is this, and we return. And else, yeah, if this, we return. Else, we return. And we're going to append in here. So we're going to say matches equals this. And we use matches here. So after we're done, we'll just say res.append matches. And now go to the next one. Now we get the other one out, but we only have mouse pad. What is mouse? Oh. We need sentinel. We need sentinel. Sentinel. So for lettering this, when I'm done, I'm going to say node word equals, no, it's not word. We need to say and equals true. Something like that. No, but you cannot be because it's going to be it's a default dict, but can you change default? You can change default dict, right? Because we need to specify that the word ends here. Yeah. Can I just like specify node end to just put the end in it? I don't know. Let's see. Print root. And yeah, we have end. I think that this is just a sentinel. Sentinel. I might have spelled it wrong. I think it's this one, right? And then we go through. So it's if and in node. Then we do this. Right? Alright, try it again. Failed again. What the? We have mouse, but we don't have mouse pad. So and in node, then matches.append. We don't return. Keep going. There we go. We don't return. We keep going because we need to Yeah, we need to keep going. Now I'm gonna try one of the other. Test case will pass. Oh, this is actually harder to code than the other one. All right, let's try this one. Submit. Will pass. Will pass too. So this is the try solution um, from the official solution. Instead of saving all the match words at each try node, we recreate, right? We recreate. But why is it so slow? Because I think I need to. What if we check this before, right? So we do this, and then we check, right? We check to pass still, because maybe we're doing a lot more matches. I don't think so though. Like if I do one DFS, right, and DFS, I do this, and then we do another one, and then say matches is 3, and then return, and do another one, it returns, and then return, then to the previous level, and we still have to go through every single one instead of. What I want is to terminate, right? To terminate while we are doing this, right? So that put it here. To terminate while we're doing this. So we're inside, and we get the first one, and we check. If it is, we just exit. And if we're done, this might make it faster. Not sure, but let's give it a shot. So what I'm saying is, I can move this to here. So we first check, and then go. Let's run it first. Yeah, because it's so slow. No, it's the same. It's the same thing. That's not the reason why it's slow. When this is true, in this part, we do DFS at the current node, right? Current node, and then search for them once. Yeah, but I feel like it's just so slow. So that's the DFS. Try solution. Get a try. Insert always to try, and then get words with prefix, which has a DFS. Result size is 3 with a term. Current word is word push back. Yep, so that's part. And then for each one, DFS all possible paths. Oh, that way you don't have to sort it initially. See if it has word plus, it's this one, and DFS for the word, and word you have the pop, yeah, but I don't have to because I don't change the word. Yeah, so I think it's the same thing. It's the same thing. But they are doing it by this. I'm doing it by the word. Yeah, it's kind of slow. Matches words at each try. We recreate each word. By DFS the try and record the letters encountered. Okay, so that's that. Oh man, I have one more solution to go through. The binary search. Sort it. The binary search for the prefix. All we need to do is to add the next three words to the result. So we sort, and then we binary search. How do you binary search on words? Sort it, iterate each character of the word, adding it to the prefix to search for. After adding the current character to the prefix, binary search for the prefix in the input. Oh, okay. So we need to find, we can compare. Yeah, we can compare. It's lexicographically, so we can compare. And once we find the match of the prefix, right? If we find the match of the prefix, then from the match to the next three words, till the prefix remains the same. Yeah. Reduce the binary search space to current start index. Least. To the fact that adding more characters to the prefix will make the next search results index be at least larger than current search index. Wow, binary search. I think I got it. Let's try it. Binary search. So this is solution 3. Binary search. Right? How do we do binary search? So products.sort. So we sort it, and then we're gonna do prefix, right? So it's before I in range len search word, right? For I in len search word, prefix is going to be search word to I plus 1, right? That's the prefix. And then we're going to binary search products, which we're going to write here. So we're going to say I and j equals 0 and len products minus 1. And we're going to say while I is smaller than j, right? I is smaller than j, mid equals I plus j divided by 2. And we want to try to find the leftmost, right? We want to try to find the leftmost, which means we want to keep the left not changing, right? And then we move the right forward. And until what? So it's like if we have a match, right? If we have a match, then we always go right going forward. Now we have a match, the left move to the match. Yes, if we have a match, so we say if products mid I plus 1 is larger or equal to prefix, right? If it's larger or equal to prefix, then what do we do? If it's larger or equal to prefix, then we say I equals mid. No. Smaller equal. Yeah, smaller equal, we move I to mid, but not mid plus 1. We move smaller to the mid, and else, when it's larger than this, then we do j equals mid minus 1, right? J mid minus 1. So I think when this get out, we're going to land at the leftmost. The leftmost product are the words that matches, right? Then we can say we'll go from the mid. No, I and J is the same, right? So from I, then we say count, not count, matches equals for k in range I to I plus 3, right? Because I don't have 3 letters. If products k, oh, we have I already. I. So this is going to be not I. So this is going to be, let's say, P. Let's call it P. So it's going to be P, and this is going to be P, and here is going to be P plus 1 equals prefix, right? So if it equals prefix, then we say product K. And once it's done, we're going to say res.append matches. And we're going to return res. Okay, so what happened? What happened? So what happened is J is not moving. So when we do the same, J is not moving. So J just moved to mid, and how is this possible? Why would it? All right, so we need to print I and J. Let's see, 3 and 4. 3 and 4. So when we start, it's an M, and 3 and 4. What's sort after sort? And we got stuck on 3 and 4. Okay, let's see. Right, sort A dot sort. Wait, 0, 1, 2, 3, 3 and 4. So we are at these two, and I think the prefix probably is I think the prefix probably is the mouse. M. Prefix is M. How did we end up here? Oh, come on. I have to terminate it. Okay. Prefix is m, right? And then we start here and here, and we say m. The mid is 0, 1, 2, 3, 4. Mid is 2, 0, 1, 2. Mid is here, right? So we go here, and p is 0, right? So it is true. So I say I equals mid. That's not correct. That's not correct. I think it has to be j equals mid. J equals mid. So like if it's the same, j equals to mid, and yeah, if I equals mid, then we just push to the right. I think it's j equals to mid. So it shouldn't be like if it's larger or equal to prefix, then we say j equals mid. Right? And that's it. We'll go back. So else, if it's, then this is going to be mid plus 1. And then what happened? Then we'll go back to j is here, 0, 1, 2. So midpoint is here. And then it still matches, so we put j here. And another one, so I think this one should be right. Res is not defined, because I never have res to begin with. And we don't have to print list out of range. List out of range. List out of range. Probably still have to print it out. So M, MO, MOU, MOU is here, 3. Oh, that has to be minimum of this, and n equals len products. So minimum of I plus 3 and n. Oh, forgot another one. There we go, now we pass. So, it's moving j, it's moving the right side, not moving the left side. Good. I think that's it. Binary search. Try it. Wow. Binary search is much, much faster. They don't have the overhead of building the try. So runtime is going to be O1 login, that's the search, right? And binary search, that's not search, that's the sort, and OM log n. That's so what we have is where n is the length of products and n is the length of search word. We hit a 136 milliseconds. It's 65%. Now that's about right. Okay, so yeah, the binary search is a much better solution. All right, that will be it for today. It's actually not that easy. I'll see you guys tomorrow. Adios.